I am Anil Kumar. Welcome to my series on probability. In this video, we'll talk about Introduction to Probability, where we are going to introduce to you many definitions, key ideas, and all the concepts which are necessary to solve problems related to probability. We'll take examples which will relate to Venn diagrams as shown here. We'll also take examples where we are going to place the information in the form of a matrix. For example, if you throw two dice, there are six numbers which could come. So these are the six numbers which are shown on one die. The other die, six numbers are also shown on the same matrix. In between, in this particular case, we are showing you the sum of the two numbers. So we'll take examples which will relate to these kinds of concepts. Let's begin with what probability really is. And let me also remind you that if you really want to learn from me, you can always send me an email on the address given here. We can have one-on-one Zoom classes and learn. Now, coming back to probability. Probability is the branch of mathematics of chance and is the study of randomness. So most of the cases we'll also see how an experiment is performed and randomly the information is picked to predict what could be the chances of getting that. It predicts possibilities of events and provides measure of the likelihood of its occurrence. So that is the basics for probability. We'll take a few more technical definitions now and we'll see how to evaluate probability of events which are simple events, single operation. We'll also look into what is a complement of an event, which is when we say what is the chances of happening this, and the complement will be what is the chances of not happening this. Mutually exclusive or disjoint kind of functions we'll look into that will lead us to the addition rule. Then we'll talk about inclusion and exclusion. We'll look into dependent versus independent, which leads to the multiplication rule. And then dependent events and conditional probability. Now, this conditional probability is a very tricky topic, but we'll have a very simple way of looking into that that will give you fairly good concept. And then we'll take up a examination style question. So let's begin with the key terms. When we talk about probability, most of the time it is one of these three kinds. It could be empirical probability. When it is empirical probability, it is based on direct observation or experiment. Theoretical probability, most of the time we are discussing theoretical probability, which is based on mathematical analysis. And then we'll have subjective probability, which is based on information, guesswork, intuition, and previous experience. Now, whenever you want to do experimental probability, which is called empirical probability, you need to perform probability experiments. And this is very critical. What should be the kind of experiment is what you need to understand. A well-defined process with number of trials in which observable outcomes or results can be recorded. That is what probability experiment is. When we say well-defined, we really mean that it could be repeated over and over again. That's kind of important. Since if you throw a dice one, you will get one of these numbers. But you cannot conclude from here that this dice will always give you that number, right? You may have to do hundreds of trials to come to a conclusion that getting a 6 on a throw of a die is actually 1 out of 6 chances. Now, when we say when you throw a dice, you get a number. Those numbers which you get, like 1, 2, 3, 4, 5, and 6, are the possible outcomes. One of them will come. Record them. Once you record them, then you can actually conclude something about it. And throwing a dice and noting the number is what is called the trial, and we are observing what we need to observe. Sometimes the question could be, well, when you throw a dice, what is the probability of getting a prime number, for example? In that case, we're looking for numbers like what? Prime numbers means 2, 3, and 5. 2, you remember, is the lowest prime number, right? So that is what we're looking into. So now that brings us to the sample space. Sample space means what are the possible outcomes? What are all the possible outcomes in this throwing or rolling a die? The possible outcomes are numbers 1 to 6. So they form your sample space. The set of all the possible outcomes in a probability experiment, that is what set of all the possible. So in this case, all the elements could be numbers 1 to 6 when you throw or roll a die. So that becomes your sample space. Now, what is a trial? Repetition of the experiment in which an outcome is produced and tallied. So you keep on throwing or rolling the dice, and whatever number you get, you put it on a chart, record it so that we could now conclude. So that is kind of important to understand. Outcomes, as we have seen, outcomes are measurable results of the experiment, whatever number comes is the outcome. Sample point, each individual outcome or element in the sample space is the sample point. Now we talk about some numbers. N of S is number of elements in the sample space. So N of S actually relates with the sample space. How many elements are there in the sample space? In the case of our experiment which we chose to roll a die, there are 6 numbers which could come, and therefore there are 6 elements in our sample space. So N of S will be 6 in that particular case. Event A. So whenever you solve a question or perform an experiment, we need to define our event. Group of possible outcomes, these are subject to sample space. So for example, in the experiment which we are doing to roll a die, what are we trying to figure out? That's what we need to define, and that will be our event. So event could be, we're looking for a number which is greater than 5, for example, right? So that could be our event. N of A is number of favorable events, right? So out of which how many are favorable. So if from the sample space we have to see how many are favorable, then the probability is the ratio of favorable over total number of elements, correct? So the probability of the event A will be possibility of that event to happen, and this is written as probability of A is equal to N of A divided by N of the sample space. So this ratio, when we calculate, you can write as percent also. Normally we leave it in fractions, but you could write to percent also to report the probability of an event happening or sometimes not happening. Now, let's understand all these with the help of example that will give you a clear idea of all the terms which we have defined. Example 1. I'd like you to pause the video, read the example, answer, and then look into my suggestions. So, example 1 is determine possible outcomes of each trial and n of space for each experiment. So, all possible outcomes is what numbers come, n of spaces, how many of them are there, right? So that number, how many, that is n of space. So this is the trial. So if the trial is rolling a die as we had been discussing, the outcomes are the numbers 1 to 6, and n of space is 6, correct? In a sample space we have only 6 elements, and this number 6 gives you that number. Tossing a coin gives you 2 options, either it is heads or tails, and so n of space is 2. Tossing 2 coins, well, now we can get a combination of head head, tail head, tail head, or head tail, tail tail. Now these 4 are our sample space elements, 4 elements. So n of space is 4. Now, what happens when you roll a pair of dice? Well, in that case, the combinations could be we have to see what comes on your first die and what is on the second die. So we can write this as a coordinate point as mentioned here, 1, 1, 1, 2, 1, 3, 1, 5, 2, 1, 6. Similarly, 2, 1, 2, 2, 2, 3. So you'll notice that there are 36 of these, which is 6 times 6. So in this sample space, we have 36 elements. So I hope this part is absolutely clear and you're ready to take up some probability examples straight off. Example 2 here is probability of an event A is given by the ratio of number of favorable outcomes to the total number of outcomes in the sample space. So probability of A is the ratio of NA and NS, right? So that is what it is. You'll find that the probability is always between 0 and 1, both included. When we say that the probability is 0, it really means that it is impossible to get this particular case. And when we say probability is 1, that means it is certain, right? So there are another two words. We say impossible and certain. So it is certain when the probability of A is equal to 1, impossible when probability of an event is 0. For example, it is impossible to get 7 when you throw dice, and it is certain that you'll get a number between 1 and 6, correct? So that is what it is. Now, let's define some theoretical probabilities and find the probability. A. Probability of tossing a head when a fair coin is tossed. Now, the word fair coin is very critical. We say fair coin means that the possibility of getting head or tail is equally likely, right? So that's another thing which we have to look into. We say fair coin, that means equally likely. So that means a fair coin. Now we could be also taking examples with biased coins where the coin could be biased so that you get more heads or more tails. It is also possible. Same in the case of dice also, the dice could be biased to give you more 6 or higher numbers or lower numbers. So most of our experiments or theoretical probabilities will always assume a fair game, uh, fair coin, fair dice. Now, the probability of tossing a head with a fair coin is what? There are only two possibilities, head or tail. So sample space n of S is 2. And you are only interested in head. So that is number 1. So 1 divided by 2 gives you the probability. So you have 50% chances of getting a head when you toss a coin. B. Probability of drawing an ace from a standard deck of 52 cards. Now, in the 52 cards, there are 4 aces. So, 4 is n of a, 52 is n of space. Any one of those 52 could be drawn, and the possibility of getting ace is only 4. So, 4 out of 52, which can be simplified as 1 over 13, is the probability of drawing an ace. C. Probability of getting sum of 7 on rolling 2 dice. Now in this particular case, when you roll 2 dice, let's go back and see our front page. Then how do you get the sum of 7? Well, we get sum of 7 as being highlighted here, 1, 2, 3, 4, 5, 6. These are the 6 options where you can get sum of 7 out of 36, correct? That makes sense for you? So that is how we are getting the answer 6 as 6 number of possibilities when you roll 2 dice, and 36 are the total numbers of sums of these numbers in a sample space, and that simplifies to 1 over 6. D. Probability that a randomly drawn integer between 1 and 100 is a prime number. Now you should know how many prime numbers are there between 1 to 100. There are actually 25 prime numbers between 1 to 100, and of course in our sample space we have these 100 numbers, and that goes in the denominator. The favorable numbers, which in our case are prime numbers this time, will be in the numerator. So 25 divided by 100, which is 1 over 4, is the probability of getting a prime number when you draw a number from 1 to 100. So I hope that gives you a good start to understand what probability really is, right? So we are always looking for favorable and the total numbers. Here is example 3 in which we'll discuss about another very important concept, and it is called complement. Complement means not that what you're looking for. Do you see that? So that is what it is. So sometimes that helps to solve questions very easily. One of the most common questions is find the probability of two students having the same birthday, having the birthday on the same date, for example, right? So that kind of question could be solved easily by complement. Now let's understand what complement is. You're seeing here a Venn diagram where we are showing a set A, correct? Everything outside this set is the complement of A, which really means not A, right? So that is clear to you. Now let's get back to the definition. Complement of an event A, which is written as A prime or A dash, is the event A does not happen. So we define an event, and in that event, we know what are the possible things we are looking into. Complement will be everything else in the sample space which was not covered in the event, right? So that is what the complement is. For example, if you are looking for numbers greater than 4, when you toss a die, then numbers 1 to 4 will be complement of that event. So A and A prime together includes all possible outcomes, right? So as we were saying, numbers greater than 4 and then numbers 1 to 4 is all the 6 numbers, correct? So the probability of getting one of these 6 numbers is 100%, correct? Or we will say 1. So that is to say that the sum of their probability is 1. Now this is a very, very important rule which you need to understand. So probability of A plus probability of the complement of A is always 1. And that also redefines what is the probability of complement of an event. It is 1 minus the probability of the event itself. So that formula really helps us in so many ways. Let's take up an example moving forward and see how to use this formula. The question here is, example 3, what is the probability that a randomly drawn integer between 1 and 50 is not a perfect square? So we're looking for integers which are not perfect squares. But can we find what perfect squares are? Well, perfect squares are 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, and so on. 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 25 is 5 square, 6 square is 36, 7 square is 49. We could include that. That is also less than 50, but 8 square is 64. So from here, clearly, we know that we are looking for these 7. You get the idea, right? Since we're looking for a number in this particular case, which is from 1 to 50. So we can list what are the possible favorable outcomes and what are the possible outcomes which are not favorable. So in this case, not favorable is easier to list, and therefore we'll define our event as let event A be equal to a perfect square. And we know there are 7 of these. And therefore, we know that the probability of this event, which is a perfect square, is 7 out of 50. Perfect. Now let's get back to our question. It says, what is the probability that the randomly drawn integer between 1 to 50 is not a perfect square? We are looking for complement of that, correct? So now you get this strategy. So the strategy clearly is, since we know that there are 7 perfect squares, it is easier to work with complement events. So we defined our event A as perfect square. and complement becomes not a perfect square. Number of elements in A, which is a perfect square, is 7, as we have just seen, right? Because the squares less than 50 are 1, 4, 9, 16, 25, 36, and 49. So, in the sample space, we have actually 50 numbers, and therefore the probability of A, which is picking a perfect square, is 7 over 50. So, complement is A prime, not perfect square. Probability of that is 1 minus 7 over 50. You got it. So, that is how we have used this particular formula, which is 1 minus probability of A, and you get your result 43 over 50. So the probability of the drawn integer between 1 and 50 not being a perfect square is 43 over 50, or you can write in percent, 86%. I hope this concept is absolutely clear. Now this is very important. So let's take another example. So it is, as you know what complement is, we are trying to see how to use this particular formula, that probability of a complement of a function is 1 minus probability of the event itself. The question here is, find the probability that the two numbers will be different when two dice are thrown. Now, what we really mean is, there are 36 options, correct? So in this particular case, think like this. So in our sample space, when two dice are thrown, we have 36 options, right? So that is a sample space. Now, how many will give you same numbers? Well, 1, 1, 2, 2, 3, 3, So on both the dice, you check the numbers. So if these are the numbers, they are same numbers, correct? How many options are there for this combination? There are only 6 options. So it is easy to figure out how many will be the elements in when you're looking for matching numbers. There are 6 of them. That is easy. So the strategy here is 36 are the total options, out of which same numbers could be only 6, correct? And these are the numbers which are listed here. So we will define our event A as same numbers. Complement of the event A prime is going to be different numbers, correct? So n of A is 6. In the sample space, we have 36. Probability of getting the same numbers is the ratio of n of A to n of S. 6 over 36 gives you 1 over 6. And so the probability of getting a different number, not same, is 1 minus 1 over 6, which is 5 over 6. So the probability of getting two different numbers on the pair of dice is 1 over 6, or around 83.3%. So with that, I think you get fairly good idea of how powerful this concept of complement is, correct? Now let's talk about another very important concept. This is called mutually exclusive event. As shown here in the event diagram, we are defining now two events, A and B, and you see they are not connected, they are disjoint. So this is also a case when we are talking about two cases where there's nothing in common. They're like totally disjoint. For example, picking up even numbers or odd numbers, right? So that is totally different, disjoint function. So that is the case. In that particular case, we'll learn another rule of probability calculations, which is the sum rule for disjoint functions, right? Probabilities of both add up, right? So now let's look into this informal way. Two or more events are mutually exclusive if they cannot happen at the same time. There are no overlaps when two or more events are occurring. These are also called disjoint functions, correct? So mutually exclusive or disjoint functions. If A and B are mutually exclusive events, then the probability of either A or B occurring is also written as probability of A or B, And also in the set form, probability of A union B is sum of their probabilities, correct? So in this case, let's look into this nomenclature. So we are saying probability of A or B, right? So the term or has come for either, and also A union B. So in that case, what are we doing? We're adding the probabilities of two simply, right? So that could be a key to understand exclusive, mutually exclusive. And this is what we're talking about, disjoint function event. Now let's take up few examples based on this. Example for A. A die is rolled once. What is the probability of rolling a 3 or a 5? Well, rolling 3 or a 5. This is mutually exclusive, right? You can get either 3 or you can get 5. That is what we mean by saying exclusive, right? So these are mutually exclusive events since both 3 and 5 cannot occur at the same time. Now, for getting 3, we have n of a as 3, b is getting 5. These are our two different events now, and in the sample space, we have 6 possible things, which is numbers 1 to 6. So probability of A or B is probability of A plus probability of B, which in this case becomes 1 over 6 plus 1 over 6, which is 2 over 6, or reduced to 1 over 3. So that is how we are going to find the probability in this particular case. So I hope it is absolutely clear, right? So we have used this particular formula that for a mutually exclusive event, what we have here is the sum of probabilities is directly giving us the or condition. Either this can happen or that can happen. Here's another example. What is the probability of rolling a 6 and flipping a red card from the standard deck of 52 cards? So there are two events. One is rolling a 6, then the second is flipping a red card. So you can define these two events as A and B as shown here, and either one of them, right, or will mean, and probabilities add up. They are mutually exclusive, and we know rolling a 6 is 1 out of 6, and flipping a red card. Half of the cards in the playing card set, which has 52 cards, are red. So 26 over 52, which is half. So half plus 6, 1 over 6 is 2 over 3. That becomes the probability of this particular event, right? Now we will talk about mutually not exclusive. That means it is not a disjoint function. As you can see here, there is an overlap. So whenever there is an overlap, we say it is not mutually exclusive. For example, you can say rolling an even number and rolling a prime number, for example, right? So when you have a dice, so when you roll a die, in that case, we are looking for even numbers. So even numbers are 2, 4, and 6, correct? And then we are looking for prime numbers, for example. So prime numbers are 2, 3, and 5. Do you see that? So what you notice here is that 2 overlaps. So it is not a mutually exclusive case. Do you understand? Something is common. Now that could lead to not mutually exclusive. And here, our sum rule will get modified because in between there is something is common, correct? So let's look into this case. That thing comes here. So now, two or more events are not mutually exclusive if they have something in common. There is an overlap when two or more events are occurring as shown in the Venn diagram. So this center portion now highlighted is the overlap, right? If A and B are not mutually exclusive events, then the probability of either A or B, this is for not mutually exclusive, occurring is probability of A or B, or written as probability of A union B, as we saw last time, sum of the probabilities of A and B, but take away the probability of A and B, the intersection part, right? Now that makes sense since, if you are doing probability of A, it could be shown as this particular area, right? This is probability of A, for example, correct? All the elements in this. Now, if I'm looking into probability of B, then do you see the center portion getting highlighted twice? So that means we counted those elements twice. So that intersection has to be taken away to get the right answer. And that is the meaning of this particular part. So now this becomes a general way of doing it, right? So that becomes a general sum rule. And of course, if you're talking about a mutually exclusive event, in that case, A intersection B will be 0. And so you're not taking anything away. You get your original formula, which we just talked about. So that becomes a general rule which could be applied whenever now you're considering either A or B or more than that. In that case, whatever is common between them has to be reconsidered, right? So in this case, if I am saying what is the probability of getting either even number or a prime number, then what are we going to do? Well, of course, even number is half, right? So the probability of even number is half, and probability of prime number is also half, 3 out of 6, and probability of even intersection prime, which is common, is 1 out of 6. Do you see that? And therefore, in our case, the probability of even or, which we could write as or also, or prime will be half plus half minus 1 over 6. You get the idea, right? So 6 common, so we get 3 plus 3 minus 1, which gives you 5 over 6 as your answer. Is that clear to you? So that is how you could find your answer for such a question. It makes sense. You actually covered all the numbers except one, right? So except one, you covered all the numbers. And therefore, we have the answer 5 out of 6. It makes sense. Perfect. So I hope that gives you a good example. Now here is your test question. So example 6, I'd like you to pause the video. Do not look into the solution which I'm giving here. Just look into the question and try to solve it. A provincial park has 120 campsites. A total of 40 campsites have electricity. Of the 25 sites on the lake shore, 10 have electricity. If a campsite is selected at random, what is the probability that it will either have electricity or be on the lake shore? So that is what you need to answer. So define your events first and see what is common between them. Add their probabilities, take away the common, and then you get your answer. So that's what I did. So we know that there are in all 120 sides. So that goes into the denominator, that is a sample space, correct? So, and then we know A, um, event A, you could divide event with electricity and on the lake shore. So we are looking for probability of having those campsites with electricity, campsites which are near the lake shore, and intersection of those. Since we know that 10 have electricity and these are on the lake shore. So that number 10 should be subtracted, that probability of 10 out of 120 should be subtracted from the sum, which is 40 over 120 and 25 over 120. So you get your result, which is 55 over 120 simplified as 11 over 24. So I hope that makes sense. So this is a short answer to your explanation. You have to write all the steps defining the events n of s, n of a, right? And then write the answer. So this is a shortcut way of your solution. Now, let's take another very important case, which is inclusion and exclusion. The probability that a student likes math is 0.7, and the probability that a student likes English is 0.2. If only 1 in 10 students like both math and English, what is the probability that a student chosen at random does not like math or English. So does not like math or English. Do you see that? So this is the examination type of a question now. So as we are moving forward, we have already understood all the concepts. So now we are getting into some questions which could be very tricky. Probabilities for liking is given to us, and probability of not liking or related are being asked for. So the complement of an event is now to be considered, right? So this is how you have to think. Now, the question here is, if A and B are mutually exclusive events, then the probability of either A or B occurring is probability of A or B equals to probability of A union B, which is probability of A plus probability of B minus probability of A intersection B, correct? This is the rule which we know. Now, complement rule which we also know is that the probability of complement of A could be written as 1 minus probability of A, correct? Similarly, probability of complement of B could be written as 1 minus probability of B. Now, these are the two formulas which will be utilized to solve the question, which is right there. I'd like you to pause the video at this stage, answer the question, and then look into my suggestions. Perfect. So let's look into the solution now. So we are given that the probability of liking maths is zero point 0.7, of English liking is zero point 0.2, and their intersection is, when we say 1 in 10, that means 0.1, right? So when we say 1 in 10, which means 1 out of 10, which is 0.1, correct? So that is the intersection of math and English, correct? Now, what do we need to figure out? Does not like math or English. So that translates. When we say does not, then definitely that complement comes. Or means union, right? And does not like math or English. That is what looking for probability. Does it make sense to you? This is what we need to figure out. Now, we are using the same formula which we learned for mutually exclusive. As you can see, it is very similar to the one which is highlighted, except for the whole formula is written for complements, right? So not that event. Perfect, but it doesn't matter. You could define the event either way. The formula is not going to change, correct? So the formula is here. Okay. Now, since you are given the function or the event which is liking and you're looking for not liking, in that case, now you have to be careful. You have to use 1 minus the probability of liking will be not liking, correct? Since the combination of liking and not liking is one probability. Perfect. So we substitute those values. So for the complement of M, we wrote 1 minus 0.7, right? For complement of E, we wrote 1 minus 0.2. And for complement of math and E will be 1 minus 0.1. Now you can calculate and get your result, which is shown here. 0.3 plus 0.8 minus 0.9, which gives you 1.1 minus 0.9, which is 0.2. So the probability that a student does not like math or English is 0.2 or 20%. So I hope this is absolutely clear. So we actually combined all the concepts which we had learned so far, many of them, in this particular example. Let's move forward and talk about another very important concept, which is dependent or independent. And this concept will also lead to a new formula for us, which we say the product rule. Now, two or more events, so two or more events, will take A and B are independent if and only if occurrence of A does not affect the probability of the occurrence of B. So we say they are independent, right? They are not affecting one another. Okay. So now drawing items without replacement is a common example of dependent event, right? So when you draw something and do not replace it, you have changed the scenario. Perfect. And therefore, the event which was performed has changed. And so the other event is dependent on what change was made. Correct? That is what it is. So based on this, here is example 6 for you. Which of the following events are independent? Explain your answer. A. A fair die is rolled 6 times without getting a 6. So you keep on rolling the die, but you never got a 6. Now, what is the probability that the seventh roll will give 6? Is it a dependent event or independent? Well, you can see for rolling a dice, how many times you roll doesn't matter. Every time you roll a die, it could give you one out of those six numbers. And so the probability of getting six is always one out of six. So it is independent event, correct? So that is how you have to explain it. Let's take the second one, which is two cards are drawn in succession without replacement from a deck of 52 cards. The first card is black. What is the probability of drawing a red card in the second draw? So, while the red card was not drawn in the first case, however, the number of cards decreased from 52 to 51. So now in our sample space, n of s is 51, not 52. So the probability of drawing the red card has been altered. So it is a dependent event. Does make sense to you? So that is how we have to identify whether the event is dependent or independent, right? Now, based on this, we'll talk about the product rule. Okay. Example 7. And before getting there, let's have a relook on dependent and independent events. If two events A and B are independent events, then the probability that both A and B, that is probability of A and B, which is also written as A intersection B, is product of their probabilities, and that is what we call a product rule for independent events, correct? So if we have to find the probability of A and B both happening, in that case we can multiply their probabilities provided it is an independent event, correct? That is very clear. So example here is Tom travels the same route to school every day. He has determined that there is a zero point 0.7 probability that he will wait for at least one red light and that there is zero point 0.4 probability that he will meet his friend Sam on his way to the school. So we are talking about two different events, waiting at the traffic signal or meeting a friend. Now these two are independent events, and therefore when we are saying and, probability to find both, and that means we can multiply these probabilities, right? So the question here is, what is the probability that Tom will not have to wait at the red light and will see his friend? So one of them we made complement. Do you see that? So that is how the questions could be very tricky. So all these examples are taken from previous test papers. Be careful when you read these questions, correct? So now when we are saying probability of not waiting, right? So that means complement of waiting, and meeting the friend, that is S, and means intersection. And since these two events are independent, we'll multiply their probabilities. Now we are given the probability of waiting, so we'll take away that probability from 1 to write down the probability of not waiting and multiply by zero point 0.4, which is given to us, to get the result, which is 12%. Clear? Part B. What is the probability that Tom will have to wait, right, at the red light and will not see his friend? So the complementary function here is not seeing the friend. So S prime, do you see that part? And we are waiting as such. So we'll take the probability of waiting, which is given to us as zero point 0.7, multiply by the complement of me not meeting the friend, 1 minus zero point 0.4, to get the result, which is 42%. You see how much difference it makes? So that is how we'll be taking into consideration independent events and complement of an event. Let's move forward and further understand independent and not mutually exclusive, right? Okay, so here is an example for you. Example 8. Let A and B be independent events. So we are saying A and B are independent really means that the product of their probabilities will be AND condition for their probabilities, correct? So We are given here, probability of A is given to us as 1 over 4. Probability of A or B is given to us as 2 over 3. We need to find the probability of B. You can pause the video at this stage and solve the question. Then look into my suggestions. Well, we are given probability of A or B, and we need to find probability of B. How do we figure this out? We're also given that these are independent events, correct? Now, the events are independent, and therefore probability of A intersection B is the product of their probabilities. Is that clear to you? And what is the union? We know the union is sum of their probabilities take away the intersection. Perfect. So we can now use the given data and get the result. We are interested in finding the probability of B. Now what is the intersection? Intersection, since we know these two events are independent, can be replaced by the product of probability of A and B. So we got an equation now which is only in terms of probability of A and B, in which probability of A is known to us, we can find the probability of B, since we know probability of A or B already. Correct? So we're substituting the known values. Probability of A or B is 2 over 3. Probability of A is 1 over 4. Probability of B is something which we need to find, minus probability of A, which is 1 over 4 times probability of B. Now it is a simple equation in which probability of B is unknown. You can actually solve this equation, isolate P of B in any way you like. I just clubbed P of B, factored it out, and then took the terms together and did all this to get the result 5 over 9. But you can follow your method to solve this particular equation. So what we get here is that the probability of B is 5 over 9. Critical thing to remember is how did we combine the two formulas, which are probability of A union B and probability of A intersection B, and also independent event, right? Which gives you the probability of A intersection B as equal to probability of A times probability of B, correct? So these are important, useful formulas. Earlier, we know that the probability of A union B is sum of the probability of A and probability of B, take away probability of A intersection B. So all these formulas, when you put them together, you can solve questions where probabilities are given to you. So make a note of these formulas on the side of your book so that you could always refer to them. Correct? Just three more examples to go, and now we're getting into a very interesting topic. Another concept, and that is conditional probability, right? So you can actually take a break at this stage, again check my video from this particular point, and then understand this concept of conditional probability. So I'll actually prefer you to take a break at this point and then reconsider all what you've learned and put them together to move forward. So now we'll talk about dependent and conditional probability. Now, two or more events that occur in a sequence, correct, are dependent if the outcome of any event changes the possible outcome of the other events, right? So if they are influencing one another, then they are dependent. That is what we have, right? Okay. So that's a complicated case. If B is dependent on A, then the conditional probability of B when A has occurred is given as, so see how we write this condition. So probability of B when A has occurred. So in this particular case, see, we are writing like this, probability of B when A has occurred. So in this particular case, this is the second event which is dependent on A, right? And this here is the condition. And this has occurred. So this has happened. We are interested in finding this probability. So we are saying, what is the probability of B when it is given This is condition given. When it is given that A has occurred, A already happened, then what is the probability? Correct? That is the case, right? So when we know something has happened, our sample space has changed. So the key area here is what does that result into? Sample space change. And that is why this probability changes, and we have now a new term which is probability of B when A has occurred, right? So I hope that point is absolutely clear. Now let's move forward. Probability of B when A, this to be read as probability of B when A has occurred. That is how you have to read it. Example 9. How do we determine if two events are independent algebraically? So that's a very interesting question from previous test paper. How do we figure out when the probabilities are given to you whether the event is independent or dependent, right? So we just came up with a formula here which says probability of B when A has occurred is probability of A intersection B when both happen, and probability of A. Since now the sample space is the sample space of A event which happened, correct? So probability of A comes in the denominator. And what both should happen, correct? So probability of B when A has occurred, right? So both should happen, so intersection on the numerator side. So that is how our general formula is. Now look here. If the event is independent, then we know that the probability of A intersection B is what? Their product. So if I replace the numerator with product of A and B, in that case clearly what happens is that cancels, the probability of A cancels, and you're left with probability of B. So if you get the condition that probability of B when A has occurred is same as probability of B, in that case, we know it is independent event. Is that clear to you? So that is a way. But if it is not so, then they are not independent, right? Then they are dependent events. So if they are different, then they are dependent events. And that's the reason why we are defining something different, correct? Okay. Now, based on this, we have two examples which are similar kinds. Now, example number 10 is for you to solve, which is two dice are rolled together. Determine the probability that exactly one die shows a 5 given that the sum is 7. So we are given a condition, sum is 7 is given to us, right? So now, and exactly 1 shows 5. So let's define our event. We are saying event A is die shows a 5. What does that mean? Well, we have two dice, so these are the possible. It could be 1 5, 2 5, 3 5, 4 5, 6 5, or 5 1, 5 2, 5 3, 5 4, 5 6. See, 5 5 is excluded. Only one of them is showing us a 5. So that is our event A. The second event, so there are 10, you can count them all. So there are 10 in numbers which are in favor of this 1 5. Event B is sum of 7. Now, how do you get sum of 7? It could be 1 plus 6, 2 plus 5, 3 plus 5, 4 plus 3, 5 plus 2, or 6 plus 1. These are the 6 ways in which you could get a sum of 7. Now, what is the intersection between the two? So, if you look into this, in that case, you find that 2 5 is common and 5 2 is also common. So, you could conclude from here that the probability of A intersection B is basically 2, right? So 2 out of total numbers are 36 when you're talking about two dice, right? So whenever you have two dice case, when you throw them, then in our sample space, we have 36 elements. So that will always come in the denominator. So is that part clear? Now let us see how do we use our formula. So we are interested in probability of A, that means it shows 5 when B has occurred and when the sum is 7. Do you see that? So we are saying probability of A, so probability of 5 when sum is 7, correct? So show 5 on one of them. I'm not writing in all, but that's what the question is. So it is the intersection of A and B, which is 2 over 36 as we just calculated, divided by the probability of B. Now probability of B can be found from here since there are 6 options out of 36. So that is how you get 6 out of 36 as probability of B. 2 out of 36 comes from here, and their ratio is 1 out of 3. And that is how you find your answer. Does make sense to you? Correct? Now, alternate method could be, let's look into this. And I'll call this as alternate way of looking into it. Alternate way is, we know that this has happened, right? So now this B is a sample space, correct? So B is a sample space. How many of these have only one 5? 2, right? So we can say 2 out of 6, which is 1 out of 3. Since we know now that this is our sample space, 7 is the sum. So these are the 1, 2, 3, 4, 5, 6 options. Out of these 6 options, there are only 2 where we have 1, 5. And so that 2 comes in the numerator, favorable. 2 out of 6 is 1 over 3. And so if you look into this angle of sample space getting changed and then work on it, you get an easier solution, which is right there for you. I hope you appreciate it. Now, another example here is example 11. A die is rolled twice. Find the probability that sum of the two rolls is greater than 10, right? So now we'll use this concept of redefine sample space also and understand it with the help of a diagram. So we are looking into now two conditions. Condition 1 is one of the two rolls is 6, and condition 2 is the first roll is 6. Okay. Now when we say one of the two rolls is 6, then here I have shown here two events. Let A be the event of sum greater than 10, right? So we're looking for event when sum is greater than 10. So in that case, we could see what are the combinations which can give a sum of greater than 10. B is the event of one of the two rolls being 6. And C is the event that the first roll is 6. So we can define like this are events, correct? Now clearly, if I'm looking at the first case, let A be the event that sum is greater than 10. In that case, how many are those cases? You could figure out with the formula. So what you could do here is you could work with the formula using these. Okay, so I'm leaving this as an exercise for students. Correct? So that you could use this formula, which you know that in this particular case, we're looking for probability of, we're saying a drive, find the probability that the sum of the two rows is greater than, that means A when B has occurred, correct? Something like this. Is what? Is basically probability of A intersection B over probability of B, correct? That is what we're looking for. So I like you to answer this question using the formula. But here I'm going to solve it using logic, right? So we are using the alternate method. So alternate method is when we are saying that the condition is that the roll is 6, and now one of the two rolls is 6. One of the two rolls is 6. So this is my, let's say, first roll. So this is 6, correct? And the other roll is 6, one of the two rolls, right? So these are the two possibilities. So we're looking into this condition, and now here, out of these conditions, we see that there are only 3 ways of getting a number which is greater than 10. And therefore, what do we have? We have total of 11, right? Let's count them. How many are these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So out of 11, we have 3 conditions which are greater than 10. So 3 out of 11 is your answer. Is that clear to you? So making this sketch helps. Now let's look into the second condition, which says the first roll. So let us say this is my first roll, correct? First roll is 6. So that is first roll could be 1, 2, 3, 4, 5 or 6. So if it is 6, then how many numbers here add up to greater than 10? There are only two cases and therefore the probability is 2 out of 6, which is 1 over 3. So from the sample space which has changed because of the condition, easily we can find the probability as shown here. This makes sense to you. So I'd like you to answer the question, understand this particular concept. Verify your answer using the formula, okay? Now here is your examination question. I'd like you to pause the video, read this question, solve, and that is the end of our video. Okay, so the example here is, there are green and blue counters in a box. There are three more blue counters than green counters in the box. Anil is going to take at random two counters from the box. The probability that Anil will take two counters of the same color is 27 over 55. Find the number of green counters in the box. Slightly complicated. Try to read the question, think about it, and then answer. Okay. Now here is how I have done. So we say let the number of green counters be 6. We know that the blue counters are 3 more. So the blue counters will be G. Let the number of green counters be G. So 3 more than G will be G plus 3, right? So we also know what is the total number of counters. So their total numbers is add them up, which is 2G plus 3. So that is our starting. We just define our variables. G is the green counters, blue counters is G plus 3, right? Now, what are we looking for? We're looking for both green or both blue. That is what we mean when we are saying same colors of two, correct? That is what we mean. Now, let us say if I pick a green, then probability of picking a green is that we have one green out of total of 2G plus 3. Now, once we have picked one green, how many greens are left? One less. So G minus 1 means one less is left, right? So left one less, correct? Once you have picked one green, one less is left. Therefore, we have G minus 1. And in the denominator also, the total number has been reduced by 1. So instead of 2G plus 3, now it is 2G plus 2. So make a change in both. Now, we're talking about an option of picking up two greens. How about picking up two blues? Well, that is also a condition. So either this or that, and they are mutually exclusive. Since you could pick either green or blue, correct? They are mutually exclusive events. So you just add them up. So for blues, we have G plus 3 blues. And when you pick one of them, we are left with G plus 2. And out of 2G plus 3, one less will be 2G plus 2. And when you do this, you get a probability. And that probability is given to you, 27 over 55. So this is the given probability. Now you have an equation with one variable G and the numbers. So you could easily find G. However, this is not an easy calculation. You can take common denominator as we did, right? And we simplified. We came up with an equation. Now see here. I could cross multiply. So what you could do here is cross multiply and solve. You could do that, correct? So that will result into the answer. But here is a neat strategy to solve this particular question in effectively very less time. What we notice here in the denominator, 2G plus 3 and 2G plus 2. These are consecutive numbers, right? So denominator is the product of consecutive numbers. So when you multiply two numbers, you should get the denominator. But 55 is 5 times 11. Two numbers doesn't work. So what I did was I multiplied both numerator and denominator by 2. And once we did that, we got 54 over 110. Now it makes sense. 110 is 10 times 11, correct? 10 times 11 is 110. So we get the value of G. Now 10 and 1 are the two numbers. So we could equate 2g plus 2 to 10 and find what g is. G comes out to be 4. Are we sure it is the right answer? Well, check the numerator. If the numerator works out to 54 for the value of g as 4, it is. So now you substitute and check. We find that it is. And therefore, we say that the number of green counters is 4. You get an idea. That's a brilliant way of solving such an equation, saving valuable examination time. And that is where I come in. So I hope you have really understood the strategies learned here. If you really want to learn from me some tricks to solve good questions, also the variety, which is very important for you to lay a good foundation, you can always send me an email on the address given. We can work it out. So I hope with that you learn. If you like and subscribe to my videos, that will be great. With this, we come to an end of our introductory lecture on probability. Mind it, it is just an introduction. We are now going to explore further a definite important criteria, which is dependent events and conditional probabilities in the next example. Then we will take up many examples related to combination and permutations and playing cards. Now, playing cards is huge in the probability, so we have different playlists for different cases where the game of poker or game with three cards will be dealt in details. So that will give you fairly good idea about probability. So once again, if you really want to learn from me, you can send an email and then we can work it out. And it's not just discrete mathematics. It could be any school level course. Thanks for your time and all the best.